Hey guys, welcome to today's video where we're revisiting this project here, which is that the XC68HC58 or J1850 variable pulse width, or also GM class 2 module that I did for the Arduino. So this lets you do your regular GM class 2 communication with an Arduino or any other microcontroller that runs at 5 volts. I mean, shoot, you could even use a computer if you had an SPI adapter, so just a little USB to SPI to run this. But yeah, this project, I'm revisiting it. This was the Rev A, and I've now made a Rev B here. I sold my last Rev A on eBay just a couple of days ago, so I am out of Rev A's. That one I need to ship, and they were interested in two, so I gotta sell them a Rev B as well. Yes, the Rev Bs are ready. I am gonna sell them, so this video is sponsored by me selling my module here. The Rev B I am not going to release the files for because I did forget to put the silk screen here that lists all the pins, and I forgot to put silk screen over here to tell what these two pins were as well. They are the same configuration as a Rev A, so if you just look at pictures of them online from the GitHub, because you're probably going to visit the GitHub anyways to get the reference code, you'll see what those pins all do. So Rev B, which I have I think 6 of them that I'm going to sell, they don't have that listing. The other thing is, and I added these two, this one connector here that can replace the screw terminal, so that way it's just the 2.54 millimeter. That way you can just do pin headers and put it on. I did kind of mess up in this design, and I forgot to keep my 2.54 millimeter spacing from this side as well, so they don't line up anymore with this. Obviously that connector didn't even exist on Rev A, but yeah, Rev C, I'll fix that as well. So Rev A, just missing silk screen, and I'm going to change one connector, just that way you know what the differences will be in Rev C if you buy them. Nothing wrong with them though, they do all work, and as you will see here in just a moment, they have a little bit more functionality than the Rev A's. So I think you guys are really going to like these. I do foresee eventually having a Rev D of it, Rev D, so the fourth one. Instead of using the PLCC configuration, I'll use that dual inline package, because I did sell these in a dual inline package. They are harder to come by though. I actually haven't found the dual inlines available anywhere online, but we do know we can salvage them from the Trailblazer instrument clusters. The Trailblazers have them right there. So this chip that has the little crystal oscillator right there, that is actually one of these in dual line. Although GM put their own part number on it, it is a 16218986 is same IC. GM used these as well in this package and some of their PCMs and stuff, but I don't know GM's part number for it. If anybody knows GM's part number, please comment it down below so that way I can see if I can find some online. I think I was able to find some of this part number online, so I'll probably order a couple of them so that way I can do a Rev D board, just because, you know, these are obsolete parts, so it's nice to have multiple sources for them, just because, you know, once they run out, they run out. And I mean, I'm not trying to make a product with these, I'm just trying to make something for the hobby space to use. And so I think this is a useful way to get into that format without using an Elm 327, because those Elm 327s really have a limited buffer, and they just they suck. Well, let's get into this video. Let's stay on topic here. Look over at the bench at the setup, see how the setup goes. Look at some code, see how the code does, and then wrap up the video. So let's take a quick look at the difference in these Rev Bs and the Rev As. First of all, I got some of these ones that obviously were remasked, but the IC does work. So I am using those on here, so just be aware that they are remasked ICs. But they do work properly. So they don't seem to be some random junk. They do actually work. But on the Rev A, I used that through-hole inductor. This time I went to an SMD inductor to kind of save some space there. And then I put a 14-volt boost power supply. So you only supply it with 5 volts. The old one you needed 5 volts and 12 volts. This time you just need 5. The pin that was used for 12 volts doesn't go anywhere anymore. So that is just a blank pin on there. I wanted to use the same connector just in case somebody had lined up a circuit board already. That way this will drop in and still work if you had made a circuit board that works with this one. The board itself is ever so slightly bigger in both the X and Y dimension, as you can see here. Hardly so in the X, but significantly in the Y dimension there. And then, yeah, so the big difference in the two is this boost converter here. So we take that 5 volts and boost it up. It can support up to 200 milliamps. However, this IC's max current it'll pull is 50, so we have a significant margin there. But yeah, we just have an inductor, a switch mode IC that has the built-in FET, and then diode, and you're supporting infrastructure that goes along with your boost. I also added the load capacitance that you're supposed to have that kind of makes the LC filter plus load capacitor that goes into the J1850. So this is the inductor and cap value are straight out of the data sheet for this IC. So that's really the overview there. You know, it's pretty much the same thing. All of these pins have the same pin assignment. However, the 12 volt pin just isn't used in this case. So same pin assignment. That way it's a drop-in replacement for the Rev A. Just hopefully if you did do it, you didn't put standoffs there because they aren't going to line up anymore. But yeah, it's plug and play, it's ready to go, and it doesn't need 12 volts. The reason why I went that route where you don't need the 12 volts is so that way you can just plug this in with an Arduino and power it off of the 5 volts supplied on your Arduino, and it'll just plug and play and work with your computer and not need that 12 volt bench power supply like you used to need. The original design of it was to with the thought process of being in a car where you're already going to have, 12 volts available. The IC, it's like that the pin can be anywhere from like 10 volts to 16, I believe, was what it's rated to. Okay, so this is the test setup, and the way I have it running right now is one of them is just writing. I believe that was this one, and the other one is just reading. So that way, one's just sending commands over and over again, and then the other's reading it. Obviously, you can transmit and read at the same time with these. I just wanted to make it a little bit simpler for my test process. Basically, if you can write, you can read with these because it's a single wire thing. You just have ground and then signal. All right, so I have the data sheet pulled up here. So we're going to take a quick look at what's going on in this data sheet on how to read this, because if you remember from the old version of this board, I never did really figure out how to read back from the chip, mostly because I didn't have very much time to spend on the project reading the data sheet and kind of digging into it because I was busy with class and work at the time. But I've had some spare time, was able to dig in a little deeper and actually figured out how to read from this chip. So we have this nice tree here that shows us it starts on about page 4-17, 4-18 on there, or around 62. Of the data sheet. Pretty much the step-by-step guide of reading from this, and gives you all of your function blocks and everything that you're going to go through on here. So you start your routine by asserting the chip select. You just insert a dummy character. It can be anything. I just used 00 as my dummy character in my example, and then once you complete it, then you should receive a status bit. If it says that there's information in there, do you continue on? And so C would be continuing on, which is right here, which then we load the flush byte in. And one of the things that I wasn't understanding last time that I saw this is when I read flush byte, I thought it meant this byte flushes the entire contents. I was thinking of this more in the sense of like discard, like you would use when you're using a serial on VB.net. When you send that discard, it just discards everything in the buffer. That's what I thought would happen if you did that. That was just my kind of misunderstanding there of, no, flush byte just means we're going to flush that one byte there and move on to the next byte in the message. And so that's what I wasn't understanding and was causing me to have problems there. So yeah, you send that flush byte, it flushes the one byte out and moves to the next byte, and just then you just continually send that flush byte till you get to the end. So all of these RFS fields are those status bits that it's talking about, telling us, hey, how much data is in this buffer, or what the status of the buffer is. So really the main ones that we need to know is querying it. Is the buffer empty? Does it contain more data? And have we reached the end? Those are kind of the three main ones you would need to make a useful program. But I actually didn't use any of them. So let's actually take a look at what I wrote, which was my quick example of reading it. And all is what it does is just sit there and try to read it. So it's just sitting there constantly sending that flush byte to read the buffer and read the entirety of it. And I'm not manipulating them into this is the message. I'm just sending them one byte at a time back to the computer. This was just kind of a quick and dirty way of trying to capture data from this chip. So all I'm doing here is sending that dummy byte and then sending the flush bytes. That way I get the status and I get my the next byte in the string, so like of a frame. So I just come through and do that, and then I just run that with a 100 millisecond delay there. So that way it's just constantly trying to read that buffer over and over. So then I have, so this one sits there writing these 3 frames over and over again with some delay there. So we'll see when we get stuck on the end that, hey, I've reached the end of the buffer on the RX. So my RX is reading faster than the TX is actually writing. But then this allows me to check two of these modules and test them and make sure they're working. Because if you can read, you can write with them, because it's all just making that SPI connection and sending. So if I can just test really one at a time on there. If one can write, it can read. So yeah, let's get these 2 Arduinos hooked up to the computer and actually start testing them. I've slowed down that read rate just a little bit there, just so that way it's less obnoxious looking in video, because I know how YouTube things will get blurry if it's moving too fast. So I went ahead and changed that. Let's go ahead and turn back on the serial monitor and connect the 2 Arduinos. Okay, so we see we get that 50, which means we have more data in the buffer, and then we've now kind of made it to the end, and then we get another message. That D0 represented that we made it to the end of the message too. So that's kind of our 3 main ones that we're looking for to turn this into reading an entire frame instead of sending it back byte by byte. Or we can make something in, say, Visual Studio in .NET that just interprets each of these bytes that it's getting and figures out if it's made an entire frame or not. So those are kind of your 2 options of handling this data right now. Obviously, I think the most applications of this are going to be, you're going to have a microcontroller that you're controlling something on the vehicle, or using it to filter something of that nature, where you're like filtering out certain messages so they don't make them to a particular module, or you're trying to add some messages. So those are kind of some options you could do with this module. But yeah, I mean, these things, they work. I'm able to test them. We have, one that's writing and one that's reading. And in this setup behind me, I actually have one of the two Arduinos hooked up to the computer. The other one's just powered off of that one. So that way, because I'm only reading with this one, the other one's just writing constantly. So that's all there is to that setup. So this one has that original example that I showed with the first version, and then the second one has this new example that's able to read. So I'll have both of these examples up on the GitHub, and then the design files for these Rev Bs, I'm not gonna put them up because I really need to do a Rev C before I put those up for you guys to be able to make your own. But you can go ahead and buy these Rev Bs that I have. There's nothing wrong with the Rev B. I just didn't put the silk screen on there, and I really would much rather have that silk screen, so that way you'll know which pens are which. Okay, so Rev A is out and Rev B is in. I hope you guys enjoyed the video. I hope you learned something. Definitely check the description for the GitHub, so that way you can start working on one of these projects, and check for a link on eBay if you want to buy one of these. They are going to be $40 plus shipping. I'm doing them in the padded envelope, so shipping's like $10 on them. So you'd be looking at roughly $50 to get one of these shipped to you. And that they're fully assembled, ready to go. I've tested them and showed you how the test setup works in this video. I really hope these things go into somebody's project, but if you also just want to buy one to support the channel, that's nice too. Any of this money that I make off of projects on the channel, I try to invest back into the channel, into either new projects or better equipment, like new microphones and stuff like that. I always appreciate y'all's support, and I hope you guys enjoyed the video. I will see you in the next one.